Hi everyone, in this video we are going to see lecture 2 of structural dynamics. So I am Dr. Leon Raj. In the lecture 1 we have seen the responses of uh, free vibrations under undamped and damped conditions. In this video we are going to see the derivation of responses for forced vibrations under damped and undamped conditions. So contents of this lecture include undamped forced vibrations under harmonic loadings. That is derivation of undamped forced vibrations under harmonic loading and the derivation of responses of damped forced vibration systems under harmonic loading. Here the forcing function is equal to F0 e power minus I omega t, and forcing function is nothing but F0 sine omega bar t. So this is the forcing frequency. This is forcing frequency. T is nothing but time period and F0 is nothing but the amplitude. So then transmissibility problems, including the support excitation problems. So basic mathematics, how to derive a complementary function for a differential equation. So you are all in the previous lecture itself have explained the response or the solution of a differential equation includes two parts. One is complementary function and another one is particular integral. So here in this video we are going to write the complementary function as C of when the roots d1 and d2 are positive, then the complementary function is equal to a e power d1t plus b e power d2t. When roots d1 and d2 are same, so that is d1 is equal to d2 equal to d, then the complementary function is equal to a e power dt into ax plus b. When roots d1 plus d2 are complex numbers, so alpha plus I beta, that is d1 and d2, then complementary function is equal to e power alpha t plus a cos beta t plus b sin beta d. So we are going to derive the responses of undamped forced vibration system under harmonic loading. So the loading you can see here is the harmonic loading. That is F0 sine omega bar t. So here this is nothing but the amplitude F0, and the time period is nothing but this is the time period. One is natural frequency, another one is forcing frequency, and another one is natural frequency. Another one is natural frequency. So this animation gives a clear picture how the forcing frequency and natural frequency are different, and it gives a better understanding for visualization. So in the previous lecture I have explained about the um, single degree of freedom and how to idealize a structure into a spring and mass system with and without dampers. So K is nothing but the stiffness, M is nothing but a mass of the system, and the forcing function is f of t is equal to f0 sine omega bar t. See, the omega bar is the forcing frequency. So we have to draw the free body diagram. The mass m is displaced to a distance of x. Then the inertia force mx double dot is the inertia force, and ks is the stiffness or spring force. This spring force and inertia force acts in the direction opposite to its motion. and the external force F0 sine omega t is acting in the opposite direction or acting along the direction of the motion. The equations of motion is nothing but mx double dot plus kx equal to F0 sine omega bar t. So this is the inertia force and kx is the spring force and this is the forcing function. So it can be rewritten as m into d square x by dt square plus kx equal to F0 sine omega bar t. So here the whole equation is divided by m. Then this term and this term will get cancelled and you will get f0 sine omega bar t by m. And just you take the x out of this differential equation. So your equation looks like d square by dt square plus k by m into x equal to f0 sine omega bar t divided by m. So this d by dt is nothing but it can be replaced with the operator called capital D. So the x is the response and response is equal to complementary function plus particular integral. So complementary function is arrived as a cos omega t plus b sin omega t. So in the previous lecture also I have explained in detail about how to arrive the complementary function. But in this lecture also I will give a brief derivation for how to arrive the complementary function. So for a complementary function, you take the right hand side is equal to 0. Then your equation of differential equation is looks like this m into d square x by dt square plus kx equal to 0. So just take the x out of the differential equations m d square by dt square plus k. Then divide the whole term by m. So this m and m get cancelled. So d square by dt square plus k by m is equal to 0. So either this term can be 0 or this term can be 0. So this term x cannot be 0. So only this term can be equal to 0. So therefore d square by dt square plus k by m is equal to 0. So d square plus k by m is equal to 0. So you get two terms actually. So d by d square, that is d square is equal to minus k by m. So then subsequently um, d equal to plus or minus square root of minus k by m. Then your d1 and d2 are looks like this, plus or minus square root of minus k by m. So here square root of minus 1 is nothing but I. So your d1 and d2 can be rewritten as 0 plus or minus I square root of k by m. So this is nothing but alpha plus or minus I beta. So your natural omega is nothing but the natural frequency. So general solution for the characteristic equation of roots d1 comma 2 is equal to alpha plus I beta is equal to complementary function, that is equal to complementary function is equal to e power alpha t plus a cos beta t plus b sin beta t, where alpha equal to 0, beta equal to omega. So your complementary function is this whole term is equal to 1 and a cos omega t plus b sin omega t is your complementary function. So your particular integral is equal to just take whole terms on the right hand side. So f0 by m into d square plus omega square into sin omega bar t. So our mathematics is saying that, so if you have the function of sin omega bar t, so then otherwise it looks like a sin a into t. So if this is the case, this can be replaced by 1 by f into minus a square. D square can be replaced as minus a square. Here the a is nothing but omega bar. So this d square should be replaced with the minus omega bar square. So this omega bar is nothing but you got from here. So your particular integral is f0 divided by m minus omega square. Just this rearrange the terms, minus omega square minus omega bar square in the sine omega bar t. So you are just take the omega square out of this term, and just take this omega square out of this equation. So you get m omega square in the 1 minus omega bar divided by omega square, omega whole square in the sine omega bar t. So here r equal to, this is force frequency ratio. This is nothing but omega is natural frequency, omega bar is forcing frequency. So your particular integral is equal to f0 by k divided by 1 minus r square sine omega bar t. So your total solution is equal to complementary function plus particular integral. So this is your particular integral. Uh, then you have to find dx by dt. So derivative of the response is nothing but a cos omega t. The derivative of this a cos omega t is minus a omega sine omega t. B sine omega t derivative is b omega cos omega t. Just we are taking the omega out, and differential of sine is cos. Differential of cos is minus sine actually. Then we are differentiating the sine omega bar t as omega bar into the constant terms into cos omega bar t. So using the boundary conditions, t equal to 0, x, that is response equal to the initial velocity, and t equal to 0, derivative of x, nothing but velocity v0. So just substitute t equal to 0 in the response x. So here the response x equal to 0. So your x equal to u0. So this is your equation 1, and substitute these terms in equation 1. So x is nothing but u0, and a cos 0 is nothing, this is 1, and this is 0, and this term is 0. So a cos 0, so your a equal to nothing but u0, that is initial velocity, sorry, initial displacement. So next, substituting the velocity, this whole term, this is equation 2. So this is the first boundary condition, this to be substituted in equation 1, and this is the second boundary condition, this to be substituted in equation 2. So v0 is equal to minus a omega sine 0 and b omega cos 0, sorry, this is 1, and omega bar f0 by k cos 0 divided by 1 minus r square. So your equation b0 is equal to b omega plus omega bar into f0 by k divided by 1 minus r square. Just take this b omega term in the left hand side, and put the v0 on the right hand side, and the whole terms b omega is equal to b0 minus omega bar um, f0 by k divided by 1 minus r square. So your whole term b equal to, just substitute this with omega, and you will get this term turns into r, and already you have 1 minus r square. So b equal to v0 by omega minus omega bar by omega f0 by k 1 minus r square. So this is nothing but b equal to v0 by omega minus r into f0 by k 1 minus r square. When the initial velocity is equal to 0, then your b, the whole term, turns into b equal to minus r into f0 by k divided by 1 minus r square. When the initial displacement is equal to 0, then the response x looks like, this is our response actually. So v u0 cos omega t minus r into f0 by k 1 minus r square sin omega t plus f0 by k 1 minus r square sin omega bar t. So here this term will be 0 when the initial displacement is equal to 0. Initial velocity is v0 and the initial displacement is u0. If these two are 0, then your response is further simplified as x equal to minus r f0 by k 1 minus r square sin omega t plus f0 by k divided by 1 minus r square sin omega bar t. Just take this constant term out of these common term out of these two terms. So just take the f0 by k divided by 1 minus r square out and sin omega bar t minus r into sin omega bar t. So this is your steady state response, and this sin omega t is nothing but a steady state response, and r sin omega bar t is a transient response. So here the steady state response and the transient response is rewritten as like this. So this steady state response exists and the transient response disappears actually. So subsequently our response is nothing but x of t equal to f0 by k sin omega bar t divided by 1 minus r square, where d is f0 by k sin omega bar 1 minus r square. So what is mean by d? D is nothing but a dynamic magnification factor. D is nothing but a dynamic magnification factor. So what is mean by dynamic magnification factor? D is the ratio of steady state amplitude divided by static displacement, static deflection or displacement, deflection amplitude of steady state response. So here the term f0 by k divided by 1 minus r square is nothing but the response. So this is actually the amplitude and the response, amplitude of the response, and your d is nothing but 1 divided by 1 minus r square. So here when the r square is less than 1, so there are two terms and r square is greater than 1. R square is less than 1 and r square is greater than 1. Your curves looks like this. When r equal to 1, the variation of frequency ratio versus dynamic magnification factor r versus d is shown in this graph, where r square less than 1, r square greater than 1 is shown here. The graph the r value is, when the r value is equal to 1, then the resonance occurs. This is the resonance. When the resonance occurs, the dynamic magnification factor shall be a maximum or near maximum. So this is the response of a undamped forced vibrations under harmonic loading. So in the next uh, section, damped forced vibrations under harmonic loading. How to derive the response of a damped forced vibration under harmonic loading. So first we have to idealize the structure into spring, mass and a damper system. So this is spring stiffness, and M is nothing but mass, C is nothing but a damping coefficient. Now we have to draw a free body diagram. So the whole mass is moved to a distance of x. Then the forces acting on this system is nothing but inertia force. Mx double dot is nothing but the inertia force. Kx is the spring force. Cx is the damping force. And the externally applied force is nothing but F0 sine omega bar t. So this is the externally applied force F0 sine omega bar t. So here the amplitude is nothing but F0, and the frequency, the forcing frequency is equal to omega bar. So this animation shows the forced vibration. So here the equations of motion is written as mx double dot plus cx dot plus kx equal to f0 sine omega bar t. So just take this whole term out of um, the x out of the whole term. So m into d square by dt square plus c into d by t in plus k into x equal to f0 sine omega bar t. So this is the response. So just you divide this with the term m. So this get cancels. So you get the c by m and k by m, d square by dt square plus c by m d by t d by dt plus k by m into x equal to f0 sine omega bar t divided by m. So either this term can be 0 or x can be 0. So x cannot be 0. X cannot be 0. That is why this whole term can be equal to 0. So x is nothing but the solution for the x is complementary function plus particular integral. So here d square um, plus c by m into d plus k by m. Here d by dt is equal to the equivalent to the operator capital D. Your complementary function is equal to e power minus omega xi t a cos omega dt plus b sin omega dt. This is a damped natural frequency. Damped natural frequency. So how to arrive this complementary function is clearly explained in lecture 1. Please refer the lecture 1 of structural dynamics. You can get the derivation of how to derive this complementary function. So next part is particular integral. So for arriving a particular integral, the whole term should be brought right hand side bottom. So f0 sine omega bar t divided by d square plus c by m d plus k by m into m. So here critical damped coefficient, that is equal to 2m omega c by ccr, that is damping ratio, where xi equal to c by 2m omega, c by m is equal to 2 xi omega, omega bar equal to r into omega. See, this omega is natural frequency. So don't get confused with omega d and omega bar. So omega is nothing but the natural frequency. Omega d is nothing but the damped natural frequency. Omega bar is nothing but the forcing frequency. So all are different. The ratio of damping coefficient divided by critically damping coefficient, that is nothing but the damping ratio. So this complete derivation is available in lecture 1 of structural dynamics. So pi nothing particular integral. Pi means particular integral. F0 sine omega bar t. C by m is rewritten as 2 xi omega, and k by m is nothing but omega square. So your particular integral is equal to F0 sine r omega. Omega bar is nothing but r omega. So r omega t divided by d square plus 2 xi omega d plus omega square into m. So again you are rewriting this, multiplying this m inside. So m d square, the denominator looks like m d square plus 2 m omega xi into d plus m omega square. M omega square is nothing but k. M equal to k by omega square equal to k by m. So nothing but omega is equal to square root of k by m. So particular integral, so here plus or minus. So particular integral equal to f0 sine r omega t divided by m into d square plus 2 psi k by omega square. So here the m is replaced with, this term is nothing but m. M is replaced with k by omega square into omega into d divided plus m omega square. Then particular integral f0 into sine r omega t divided by m d square plus 2 psi into k by omega into d plus m omega square. So m omega square is nothing but k actually. So this is nothing but k. So you can rewrite the equation as f0 sine r omega t divided by m d square plus 2 xi k divided by omega into d plus k. So further it is rewritten as if your particular integral on the is to be found for the forcing function r omega, that is equal, it's nothing but if it is a sine a t, then your particular integral can be 1 divided by f of minus a square. So this can be, this d square term can be replaced with this r omega minus, that is minus r omega whole square. So this term is replaced here. So f0 sine r omega t divided by minus m r omega whole square plus 2 xi k divided by omega into d plus k. So particular integral equal to f0 sine r omega t minus k r square, that is m omega square is nothing but m omega square is nothing but k. So plus r into, sorry, 2 into xi into k divided by omega into d plus k. So it is further written by taking the k out of the term. The k is taken outside. So f0 sine r omega t k into minus r square plus 2 xi divided by omega d plus 1. So it is further written as f0 by k sine r omega t divided by 2 psi divided by omega into d plus 1 minus r square. So further, if your denominator is 1 divided by x plus a, and you want to convert this into 1 divided by x minus x square minus a square, then you have to use the trick of multiplying this 1 divided by x plus a by x minus a divided by x minus a. So now your term will be x minus a divided by x square minus a square. So you want to convert this term 1 by x a into 1 by x square minus a square. So a similar term. So this d should be converted into a d square term. So that is why uh, we have taken this step. So this whole term, the denominator is multiplied with the numerator and denominator by change of sign. So here 2 psi omega divided by omega into d minus 1 minus r square divided by 2 psi divided by omega d minus 1 minus r square. So this is one term and this is another term. So your particular integral, so what you expected is d square, which we could able to get, and we multiplied the whole term with the numerator 2 psi divided by omega into d minus 1 minus r square sine r omega t divided by 2 psi divided by omega whole square d square minus 1 minus r square. So just you multiply this whole term with this d square should be replaced with r omega. So here the r omega is replaced here. So here this is r omega square, and you can multiply this sine r omega t these places. So you will get 2 psi omega d in the sine r omega t minus 1 minus r square sine r omega t divided by 2 psi omega whole square in the r omega square. So you have to substitute minus r omega square. So this minus and minus r omega square get be positive. Uh, um, Sorry, this minus and this minus were taken in the front. Uh, so this is the minus. So divided. So the denominator term is 2 xi divided by omega whole square r omega square plus 1 minus r square. Then this whole term can be rewritten as minus f0 by k in the 2 xi omega d by dt sine r omega t. So this d is nothing but d is an equivalent term for d by dt. So this d by dt, the sine r omega t needs to be differentiated one time. So in the second term, differentiation is not required. At 1 minus r square sine r omega t, the differentiation is not required. So here the sine r omega t is differentiated as cos r omega t, and the term r omega is taken in the front, and this omega and next omega is get cancelled. So your whole term looks like f0 by k minus 2 r xi cos r omega t plus 1 minus r square sine r omega t divided by 2 psi r square plus 1 minus r square. Just take this then particular integral turns like f0 by k minus 2 r xi cos r omega t plus minus 1 minus r square sine r omega t divided by 2 xi r whole square plus 1 minus r square the whole square. So here this r omega and r omega is replaced with omega bar. So you are rewriting it as f0 by k minus 2 r xi cos omega bar t plus 1 minus r square sine omega bar t. So the whole term can be rearranged like f0 by k into 2r xi, that is minus 2r xi divided by 2 xi r whole square plus 1 minus r square into cos omega t plus 1 minus r square divided by 2 xi r whole square. So this is the first term and this is the second term. If a term called x plus a divided by x square plus a square, then it can be rewritten as x by a, x square plus a square plus a by x square plus a square. So this is what written here. So just taking the whole term, the constant terms out, f0 by k into 2 xi r whole square plus 1 minus r square into uh, uh, minus 2 r xi cos omega bar t plus 1 minus r square sin omega bar t. So taking the right angle triangle, the hypotenuse term is the opposite side is 2 r xi, the adjacent side is 1 minus r square, and the hypotenuse is equal to square root of 1 minus r square whole square plus 2 r psi square. So this is the hypotenuse. So tan theta is equal to, this is your opposite side, so this is adjacent side, and this is hypotenuse. So your tan theta is equal to opposite side by adjacent side. So your opposite side is 2 r xi divided by 1 minus r square. So theta is nothing but tan inverse of 2 r xi divided by 1 minus r square. So sin theta is equal to 2 r xi divided by, that is opposite side by hypotenuse. So this is the opposite side and this is hypotenuse. Hypotenuse. So cos theta is equal to adjacent side by hypotenuse. Here adjacent side is 1 minus r square divided by square root of 1 minus r square whole square plus 2 r xi whole square. So the terms can be rewritten as 1 minus r square is equal to cos theta into hypotenuse. 2 r xi, this is adjacent side and this is opposite side, sin theta into hypotenuse. So using the term mathematical formula, sin a minus b is equal to sin a cos b minus cos a sin b. So your particular integral can be rewritten as this term can be substituted with the values we obtained in the previous lines. So your particular integral is equal to f0 by k into 2 xi r whole square plus 1 minus r square whole square into sin theta, that is minus sin theta square root of 1 minus r square plus 2 r xi square cos omega bar t plus cos theta into square root of 1 minus r square whole square plus 2 r psi omega 2 r psi the whole square into sin omega bar t. So this is a common term here and this is a common term here. So this can be taken out and the square root term can be striked out. So here it can be rewritten as instead of sine this sine theta cos omega bar t plus cos theta sin omega bar t. So f0 divided by k into the whole term can be taken outside, and it is, and here the root term will come. So actually here also this term will come here, 1 minus r square whole square plus 2r xi whole square. So this term is striked out. Sorry, just 1 minute. This sine omega bar t cos theta minus sine omega bar t sin theta. So it can be rewritten as sine omega bar t minus theta. So sine a minus b form is written here. So which one is a? Omega bar t is nothing but a, and theta is b. So sine omega bar t minus theta, that is sine a minus b. So your whole term is written as f0 divided by square root of 1 minus r square into 2r psi the whole square. So it is further simplified and written as f0 by k 1 minus and 1 divided by 1 minus r square plus 2r psi square sine omega bar t minus theta. So only this term is taken outside for a reason. So x is nothing but a complementary function plus particular integral. So this is your complementary function and this is your steady state. The transient state disappears. So this animation is shown here. So this is a homogeneous solution for the differential equation. So here the So here the particular solution looks like this, and the transient state solution response looks like this, and this is the total solution. So total response of a damped forced vibration looks like this. So damped forced vibrations under harmonic loading. So dynamic magnification factor D is equal to steady state amplitude divided by static deflection. So your response x equal to 0 plus that is a transient response, we are just making it as 0, and your steady state response equal to f0 by k into 1 minus r square plus 2r xi square. So your dynamic magnification factor D equal to f0 by k into 1 divided by 1 minus r square whole square plus 2r psi whole square divided by f0 by k. So this term and this term get cancelled, and your dynamic magnification factor is equal to 1 divided by square root of 1 minus r square plus 2r psi the whole square. What is in the dynamic magnification factor? How much the steady state amplitude is magnified with respect to the static deflection. This is nothing but a dynamic magnification factor. In the coming lessons, we will when we solve some problems, you can understand in a better way what is in the dynamic magnification factor. So this ratio of forcing frequency, the ratio of forcing frequency to natural frequency is nothing but frequency ratio. The variation of dynamic magnification factor versus frequency ratio is drawn here. So let us plot with the points available with us. So if you substitute r equal to 1, your d equal to 1 by 2 into xi. So if r equal to 1, xi equal to 1, then d equal to 0.2. when r equal to 1. R equal to 1 is nothing. This is the r equal to 1. R equal to 1 and xi equal to 0.1, that is the damping coefficient is 0.1 when d equal to 5. Then r equal to 1 when xi equal to 0.002, d equal to 50. So you can see a significant change in the d when the dynamic magnification factor, when there is a damping, and when the frequency ratio is 1, here the resonance occurs. So this is the frequency ratio. This is nothing but the frequency ratio, and this is nothing but the dynamic magnification factor. Dynamic magnification factor. So for different psi values, that is different dynamic means for different damping coefficients, when xi equal to 1, this is nothing but critical damping. In this critical damping, so your dynamic magnification factor vary with respect to r value is shown here. For different psi values, the dynamic magnification factor is maximum at r equal to 1. So resonance occurs when the natural frequency is equal to the forcing frequency. For different psi values, for different psi values uh, uh, so for different psi values, for different damping coefficient, uh, when the frequency ratio is equal to 1, damping dynamic magnification factor increases, or uh, it amplifies more. When r equal to 0, then d equal to 1. There is no dynamic magnification, so d equal to 1. When xi equal to 1, the dynamic magnification factor is equal to 1 divided by 1 minus r square the whole square plus 2r square. So when xi equal to 0, the response is looks like the derivation we obtained in the previous slides, that is 1 divided by 1 minus r square. So now the next derivation, that is damped forced vibrations under harmonic loading, that is f0 e power minus I omega t. So these explanations I have given in the previous slides. So here the forcing function is nothing but f0 e power minus I omega t. So here the equations of motion is nothing but mx double dot plus cx dot plus kx equal to f0 e power minus I omega t, omega bar t. So your differential equation m into d square by dt square plus c into d by t plus k into x equal to f0 e power minus I omega bar t. Just divide this with m. So you get this equation. That is this, either this term can be equal to 0 or this term can be equal to 0. As x cannot be equal to 0, this term only be equal to 0, and your complementary function is equal to e power minus omega, e power minus omega xi t a cos omega dt plus b sin omega dt. So this omega d is nothing but damped natural frequency. Omega is nothing but frequency, natural frequency. So your particular integral is equal to f0 e power minus I omega bar t divided by d square plus c by m into d plus k by m into m. So of course these are all the terms I explained in the previous slides. Also in the lecture 1 I have given a detailed derivations. So omega bar equal to r omega. So particular integral equal to f0 e power minus I omega bar t divided by d square plus 2 xi omega into d plus omega square into m. So this if the function is e power I omega t omega bar t, then the it can be replaced with same. So here the uh, d should be replaced with this term. So pi is equal to f0. So here this common terms omega square equal to k by m, m omega square is equal to k, and m equal to um, k by omega square. So instead of c by m omega square is replaced with k. So m into d square uh, plus 2 xi k divided by omega d plus k. So this d square and d, these two terms should be replaced with minus ir omega. So this term should be replaced with minus ir omega, and this term should be replaced with minus ir omega. So this is d square term and this is d term. So again you just get the expressions e power minus ir omega t divided by minus r square. Just take this k term out of the parenthesis. You will get f0 by k e power minus I r omega t divided by minus r square minus I into 2r xi plus 1, and just by taking this term minus I into 2r xi divided by 1 minus r square. So as I said earlier, if you are having a term x plus a and you want to convert this term into 1 divided by x square minus a square, then this term should be multiplied with x minus a divided by x minus a, and you will get 1 divided by x minus a square. So same thing, we want to convert this I term into I square term, so that this disappears. So we multiplied this the whole term with minus. So this term is minus 2 r psi minus 1 minus r square. So just multiply this numerator and denominator with this um, denominator term by sign change, and you will get the expression looks like this. So this minus I 2r xi whole square and the I square get disappears. So it turns into 2r xi the whole square into 1 minus r square, and the minus and this minus is taken out, and this I square is equal to minus 1. So that's why this I square equal to minus 1. So this minus the minus is taken out, and the numerator terms stays as it is. So just multiply this whole term e power minus ir omega t inside this, and you will get 1 minus r square plus this is I into 2 r xi into e power minus ir omega t. So this is your angle theta, and if horizontal term is that is uh, adjacent side is 2 r xi and opposite side is 1 minus r square, and square root of 1 minus r square whole square plus 2r xi whole square is nothing but hypotenuse, and your tan theta is equal to opposite side by adjacent side, opposite side by adjacent side, adjacent side, and sin theta is equal to um, opposite side by hypotenuse, cos theta is equal to adjacent side by hypotenuse. So this is what written here. So your 1 minus r square equal to sin theta plus sin theta in the hypotenuse, and 2r xi is equal to cos theta in the hypotenuse, e power I theta equal to sin theta plus cos theta. So your sin theta and cos theta terms should be replaced with the existing terms. So this sin theta, you know, from this you can find the sin theta and cos theta. 1 minus r square divided by, so this is your sin theta and this is your cos theta. So e power I theta is equal to, it is restructured as 1 minus r square plus I into 2 r xi. So your particular integral equal to f0 by k 1 minus r square into plus I into 2 r xi into e power minus ir omega t divided by 2 r xi whole square into 1 minus r square into whole square. So again, this whole term is rewritten as below. So uh, the term particular integral is equal to f0 by k 1 minus r square plus I into 2 r xi divided by square root of 1 minus r square whole square plus 2 r xi the whole square e power minus ir omega t divided by 1 minus r square whole square plus 2 r xi whole square. So e power I theta. So this whole term we have derived here, and this term can be rewritten as like this. So sorry, not this term, and this term can be rewritten as here. So e power I theta uh, divided by square root of 1 minus r square whole square plus 2 r xi whole square. So it is further written as e power I theta minus ir omega t divided by square root of 1 minus r square whole square plus 2 r xi whole square. So the response is further derived, that is particular integral is further derived as f0 by k divided by 1 minus 1 divided by square root of 1 minus r square whole square plus 2 r xi whole square in the e power minus I omega bar t minus theta. So this part is transient state, and this part is steady state. So this steady transient state, we are making it as 0. That is, the complementary function is the transient state, and the steady state is nothing but the particular integral, and the response looks like this. So this is the transient state. So this is complementary function, and this is particular integral, and further complementary function particular integral superimposed as like this. So your dynamic magnification factor is nothing but steady state amplitude divided by steady static deflection. So so this part is your dynamic magnification factor. So this whole term get cancelled. So this is your D. So how this D is varies with respect to the various damping ratios I explained in the previous uh, slide, that damped forced vibration responses under harmonic loading where the forcing function is f0 sine omega bar t. So if your damping ratio is equal to 1, this is critically damped, and this is the forcing frequency R equal to 1. R equal to 1. So this is nothing but resonance. So here the dynamic magnification factor for different psi values 0.001, 0.002, 0.07 for 1, 2, 3, 4 and 5 for different psi values. The graphs were drawn. The dynamic magnification factor versus frequency ratio is drawn here. When R equal to 1, D equal to 1 by xi, R equal to 1, xi equal to 1, D equal to 0.2, R equal to 1, when xi equal to 0, 0.1. Actually, these are all input. Just to explain this, I am giving this. Then D equal to 5, when R equal to 1 and xi equal to 0.01 and D equal to 50. So you need two terms actually to get the dynamic magnification factor. So R and psi. When R equal to 0, D equal to 1, and R psi equal to 1, D equal to, this is the expression 1 divided by 1 minus R square whole square plus 2 R square. When psi equal to 0, the dynamic magnification factor looks like an undamped dynamic magnification factor. Now we are going to see the support excitation problems. So here the support is also excited. The xst, that is equal to f0 sine omega t. M is nothing but the mass, K is spring stiffness, C is the damping coefficient. The mass is moved to a distance of x. At the same time, the support is moved to a distance of xs. Mass moved to a distance x and the support moved to a distance xs. So f of t equal to f0 sine omega bar t, and this is same. This is the inertia force, and the spring force looks like this. Inertia force is nothing but mx double dot. Spring force is nothing but k into x minus xx, and damping force uh, um, is equal to c into x dot minus xs dot. Equations of motion for support excitation: m x double dot plus c into x dot minus uh, xs dot plus k into x minus xs equal to not 0. Actually, this is for free vibration. For applied harmonic force, xst is equal to f0 sine omega bar t. So here the omega bar is not clearly written here. So your response is like m into d square x by dt square plus c into dx by dt minus dxx by dt plus k into x minus xs equal to 0. So just you will get the there is no here there is no any external forces, but at the same time, okay, um, actually this is x of there is no force in the external force applied force. Only the support is excited, that is x s of t, that is equal to f0 sine omega bar t. So this is support is excited. So your differential equation is rewritten as m into d square x by dt square plus c into dx by dt plus kx equal to c into dxs by dt plus k into xs. So here x s of t is nothing but f0 sine omega bar t. Just substitute this here as f0 sine omega bar t, and this x is also like this. So x s of t equal to c into d by uh, dt into f0 sine omega bar t plus k into f0 into sine omega bar t. So c into f0 omega bar into cos omega bar t uh, plus k into f0 sine omega bar t. So your uh, opposite side is c omega bar, and adjacent side is k, and your hypotenuse is square root of c omega bar square plus k square. So your tan beta is equal to c omega bar divided by k. Sin beta is equal to c omega bar divided by square root of c into omega bar square plus k square. Cos beta is equal to k by uh, square root of c into omega bar square plus k square. So c omega bar equal to sin beta into hypotenuse, and k equal to cos beta into hypotenuse, and your differential equation is can be rewritten as m into d square x by dt square plus c into dx by dt plus kx equal to f0 into c omega bar cos omega bar t plus k into sin omega bar t. So your response, that is differential equation, can be rewritten as the right hand side is f0 into square root of c omega bar square plus k square into sine beta cos omega bar t plus cos beta sine omega bar t. So this can be rewritten as sine a plus b is equal to sine a cos b plus cos a sine b. So this whole term can be rewritten as sine into omega bar t plus in beta. So this term is nothing but f s. So f s equal to square root of f0 into square root of c omega bar square plus k square. So f s equal to f0 into c r omega whole square plus k square, and f s equal to f0 into square root of c square r square omega square m divided by m plus k square. So C by CCR is equal to xi, and xi is equal to C by 2m omega, m omega square equal to k, omega bar equal to r omega, C by m is equal to 2 psi omega. So it is further Fs is further written as F0 equal to C square r square k m divided by m square plus k square, and it is further written as C by m square m whole square r square km plus k square. So Fs equal to F0 into 2 xi omega whole square r square km plus k square. So it is Fs equal to F0 is equal to square root of 2 xi r whole square k square plus k square. So k is taken as constant into outside. So Fs equal to F0k square root of 2 xi r whole square plus 1 tan beta is equal to c by k omega bar equal to CR omega m divided by mk. So turn beta is further written simplified as 2 xi omega rm omega divided by k. So turn beta is equal to 2 xi rm omega square by m, that is nothing but 2 xi r. So your equation is further simplified as m into d square x by dt square plus c into dx by dt plus kx equal to fs sine omega bar t plus beta. So if your term is sine into a x plus b, then your particular integral can be written as 1 by f into function of minus a square. So the equation is further the response differential equation. How to solve this differential equation I have explained in the previous slides, also in the lecture 1 of structural dynamics. So here the response is further simplified as fs by k into 1 divided by square root of 1 minus r square whole square plus 2 r xi the whole square sine omega bar t plus beta, that is ax plus b minus theta. So theta is nothing but the phase angle change. X s of t is nothing but f0 sine omega bar t. X s of t max equal to f0, that is nothing but the amplitude. So x of t divided by xs of t is nothing but fs by k square root of 1 minus r square whole square plus 2 r xi the whole square in the sine omega bar t plus beta minus theta divided by f0 sine omega bar t. So it is x of t divided by xs of t max. This t max is nothing but f0. So it is further simplified as x of t divided by xs t max is nothing but square root of 2 xi r square plus 1 divided by square root of 1 minus r square whole square plus 2 r xi whole square into sine omega bar t plus beta minus theta. So transmissibility is nothing but xx of t amplitude, that is square divided by xs of t max, that is equal to square root of 2 xi r whole square plus 1 divided by 1 minus r square plus 2 r xi whole square. So if r equal to square root of 2, transmissibility equal to 1 actually. So irrespective of r, if your uh, 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 irrespective of if your r equal to square root of 2 irrespective of damping ratio, um, if your r equal to square root of 2, then the transmissibility is equal to 1 actually. For different r equal to 1, when xi equal to 1, the transmissibility is equal to 1.11. This is the phase angle change. So you can see the how the red line varies with respect to horizontally and vertically, how the red line varies, and how the uh, um, blue line varies. You can see the whole circle is moving. Tan theta is nothing but the tangent. So here the nice animation is shown here, how the phase angle changes actually with respect to the theta. So when the phase difference is uh, uh, 360-degree, there is no phase change. When it is 180-degree, it is out of phase. When it is a 90-degree, and there is a phase change. The transmissibility versus frequency ratio is shown here. So irrespective of damping ratios of 0.001, 0, 1, 0.02, 0.7 and 1.0, your transmissibility, that is transmissibility equal to 1 for r equal to square root of 2. So when you design this, so you can the force transmitted when you design r equal to square root of 2, the dynamic transmissibility will be 1 actually. So this is the phase change from 0 degree to 180 degree. There is a phase change at 90 degree. So this is the tan theta. So this is when xi equal to 1, this is psi equal to 1, and this is xi equal to 0.7, and this is psi equal to 0.2, and this is xi equal to 0.01, and this is when xi equal to 0.001. So this is the variation of phase angle with frequency ratio is shown here, and the transmissibility variation of transmissibility as frequency ratio is shown in this figure. So the reference books are Dr. A.K. Chopra, the Dynamics of Structures, then Mario Paz, Structural Dynamics, then Som's Outlines for Mechanical Vibrations by Professor Graham Kelly. Thank you.